So to build such an invariant, let's go back and consider our special relativity dictionary for space and time transformations. So if we have time as measured by an observer S prime and time and space coordinates as measured by an observer S prime, and time and space coordinates as measured by an observer S. And we'll assume, without loss of generality, that the observer S prime is moving with respect to observer S with a speed v along the positive x direction. So in general, the transformation then is related by a matrix, okay, which we called lambda v. So it's some matrix that depends on the speed v of the frame S prime relative to the frame S. And we saw that we could write the transformation in this form: gamma minus gamma beta 0, 0 minus gamma beta gamma 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And this was, of course, relied on the fact that we're using a special origin for the observer S prime. We're assuming that the origin of S prime is chosen such that T prime is 0 and X prime, Y prime, Z prime are 0 at the point where T is 0, X is 0, Y is 0, Z is 0. That is, this spacetime point and this spacetime point are the same. But even if we don't choose these two spacetime points to be the same, we've seen that we would also have some kind of offset, okay, plus a possible offset, where this offset matrix is just a matrix of constants which doesn't depend on the speed v. It just depends on the choice of origin that observer S prime makes of their space-time coordinates. However, if we consider time intervals or distances between two space-time points, so let's consider the space-time point which is at as seen by observer S, which is at T1, X1, Y1, and Z1. And let's consider another space-time point, which is T2, X2, Y2, and Z2. So you've located a particular point in space at a particular instant of time, and you can ask what's going on over there, and another point in space and another point in time. And these points in space and time are measured in the reference frame S. Now, observer S prime has a different description of that same space-time point. So let's suppose that they describe the point 1 by the coordinates T1 prime, X1 prime, Y1 prime, Z1 prime, and T2 prime, X2 prime, Y2 prime, Z2 prime to describe the second space-2 point. So there is only one physical point in space, but there are different descriptions of this physical point depending on which observer you're talking about. Now, the transformation between the difference between these two space-time points, that is, if I take T2 prime minus T1 prime and X2 prime minus X1 prime and Y2 prime minus Y1 prime and Z2 prime minus Z1 prime, and ask how is this related to T2 minus T1, X2 minus X1, Y2 minus Y1, and Z2 minus Z1. The first thing that you would see is that the offset matrix doesn't really matter when we take the difference between two space-time points. So the choice of origin will be irrelevant. And therefore the transformation matrix in this case would be minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1. Okay, and gamma, of course, let me just remind you, is 1 over the square root of 1 minus v squared by c squared, and beta is v by c. And we've also seen that we could rewrite things in terms of eta, where eta is the rapidity, where we've defined tan hyperbolic of the rapidity as beta. Okay, in this case, if we use the rapidity, then what we would get is our transformation matrix looks a little different. It looks like cosh eta minus sinh eta cosh. Now clearly this dictionary, okay, tells us that time intervals change because the time interval t2 prime minus t1 prime is related not just to the time interval t2 minus t1, but it also depends on the spatial separation x2 minus x1. And similarly, the spatial separation x2 minus x2 prime minus x1 prime depends both on the time interval of separation between those two spacetime points as well as the spatial separation of those two spacetime points as described by observer S. However, let's consider a different quantity. Let's consider the quantity c times t2 minus t1 prime, the whole square, minus x2 prime minus x1 prime, the whole square, minus y2 prime minus y1 prime, whole square, minus z2 prime minus z1 prime, whole square. And let's ask how observer S describes the same quantity. So in observer S's definition, this quantity, okay, so we can just use our dictionary to rewrite t2 prime minus t1 prime and x2 prime minus x1 prime and y2 prime minus y1 prime and z2 prime minus z1 prime in terms of the quantities seen by observer S. So again, using rapidity, because that's the easiest thing to do, we can write this as cosh eta times c t2 minus t1 plus sinh eta, minus sinh eta x2 minus x1. That's what t2 prime minus t1 prime would be, whole square. And then if we consider the second term over here, this would be minus sinh, or minus of, within brackets, minus sinh eta c times t2 minus t1 plus cosh eta times x2 minus x1 whole square minus y2 minus y1 whole square minus z2 minus z1 whole square. And let's simplify this more. So if we write this out by expanding the square, the first thing that you could see is when we expand the square, we will get two cross terms. Okay, so we'll get one cross term that is the product of this term with this term, and we'll get another cross term from the second term in brackets, which is the product of this term with this term. And you can see that because of the relative minus sign over here, those cross terms will exactly cancel out with each other. Okay, so we only have to consider the non-cross terms. That is, we won't have any terms which have a cross product between time and space intervals. So now if we write this out, we would get cosh square eta from times, so let's write the coefficient of ct1 minus t2 the whole square. The coefficient of this would be, there would be a cos square eta from the first bracket, and from the second bracket there would be a minus, the minus sign comes from here again, sinh square eta. And now let's write the coefficient of x2 minus x1 the whole square. The coefficient of that from the first bracket is plus sinh square eta, and the coefficient from the second bracket is cos square eta, again with this minus sign. So minus cos square eta minus y2 minus y1 whole square minus z2 minus z1 whole square. So if we write this out, now we can use the fact that cos square eta minus sin square eta is 1 no matter what the value of eta. Okay, this is just an identity, just like the trigonometric identity of cos square theta plus sin square theta is 1. So just to remind you, cos eta is e to the eta plus e to the minus eta by 2. Sinh eta is e to the eta minus e to the minus eta by 2. And cos square eta minus sin square eta is 1 no matter what the value of eta. So therefore, what we have is that this expression is just c t1 minus t2 whole square minus x2 minus x1 whole square minus y2 minus y1 whole square minus z2 minus z1 whole square. So what have we proved? Well, let's consider the quantity we started with, okay? And what we see is that the quantity that we started with, which is c times t2 prime minus t1 prime whole square minus x2 prime minus x1 prime whole square minus y2 prime minus y1 prime whole square minus z2 prime minus z1 prime whole square is the same as the same quantity, but expressed using the coordinates in frame S. So we see that we have given two space-time points, there is a point P1 and a point P2. Any inertial observer can construct the quantity where they take the description of the time and space coordinates of P1, the time and space coordinates of the point P2, and they take the difference between the time coordinates, square them, and they take the difference between the spatial coordinates, square them, but they construct this slightly strange looking quantity, which is the time difference square times c square minus the spatial difference square minus in all directions. So minus x2 prime minus x1 prime square minus y2 prime minus y1 prime square, and so on. And each observer can do this in their own coordinate system. But the net result is that they would get exactly the same quantity. They would get the same number associated with these space-time points. So that is to say that any two observers would get a single number associated with these two space-time points, and that number would be the same. Okay. So this allows you to calculate a single number from two space-time points, and all observers agree on the value of this number. All inertial observers. All right. So this quantity that we've constructed is called a space-time interval. And is sometimes denoted as c square delta tau square. Okay, if the spacetime interval is positive, then of course delta tau is a real number. However, if the spacetime interval, you can see that it's possible for the spacetime interval to be both positive or negative, right? It doesn't have to be positive, it doesn't have to be negative. It can be either, depending on the choice of spacetime points that you make. So sometimes it's denoted in this way. It's denoted as c square delta tau square. This is typically the description if the spacetime interval is positive. And if the spacetime interval is negative, we define it to be c square or minus c square delta sigma square. Okay. Of course, you can still define it to be c square delta tau square even if the spacetime interval is negative. In that case, delta tau would be imaginary. And if the spacetime interval is negative, is positive, you could also define it to be minus c square delta sigma square. But in that case, delta sigma would be imaginary. Okay, so if you choose these definitions, that is, you choose it to be defined as c square delta tau square if the spacetime interval is positive, and you choose it to be minus c square delta sigma square if the spacetime interval is negative, then delta tau and delta sigma are positive. Okay, so with these definitions, delta tau is real and delta sigma and of course if the spacetime interval is 0, then it doesn't matter which definition you use, delta tau would be 0 and delta sigma would be 0.